All right, so you know how sometimes you have a tool that's really useful, but you think, man, if only I could do just this one more thing.
Yeah, like you wish you could add some kind of special attachment to it. Like take a basic Swiss Army knife.
Yeah.
It's got a lot going for it, but what if you could slap on a tiny saw blade or a super precise screwdriver when you needed it?
Exactly. And turns out that's kind of what computer scientists do with data structures through a process called augmenting. They're basically souping up these data structures to make them even more powerful and efficient. And for today's deep dive, we're jumping into Chapter 17, Augmenting Data Structures, to explore just how they pull this off.
It's really quite clever and surprisingly elegant. We're going to zero in on two specific examples, order statistics and interval trees.
Yeah.
We'll see how adding just a little bit of extra information to these already efficient structures can unlock some really impressive new capabilities.
Our mission, should we choose to accept it, is to demystify this whole augmentation thing. And we're going to do it in a way that doesn't require a PhD in computer science, I promise. But first, maybe you can give us a little refresher on what a data structure is exactly, like for those of us who might have forgotten since our intro to CS class.
Ah, good point. At its core, a data structure is simply a way of organizing data in a computer so we can access and manipulate it efficiently. Different types of data structures have strengths and weaknesses depending on the task at hand. Think of it like choosing the right tool for the job. You wouldn't use a hammer to screw in a bolt.
Makes sense. So are we talking about tweaking any kind of data structure when we say augmenting?
In theory, yes. But in practice, there are certain structures that lend themselves really well to this kind of enhancement. And one of the most popular choices is the red-black tree.
Ah, the red-black tree. Now that rings a bell.
Yeah, it's this super useful self-balancing binary search tree. The way it's set up, even when you have tons and tons of data, operations like searching, inserting, and deleting can still be done in logarithmic time. That basically means the time it takes doesn't skyrocket as the amount of data grows. It stays relatively fast.
I see. So it's like a super organized filing cabinet that's really good at finding stuff quickly, even when it's overflowing with files.
Exactly. And it turns out that red-black trees are a fantastic starting point for augmentation because they're already so efficient at their core tasks.
Okay, so let's dive into this first augmentation example, dynamic order statistics. I gotta admit, the name sounds a bit intimidating.
Maybe, but it's really not as complicated as it might sound. The chapter frames it as this classic problem. Imagine you have a big set of data, and it's constantly changing. New elements are being added, old ones are being removed. It's all very dynamic.
Okay, I can picture that. Lots of data in flux.
Now, in this scenario, a common task is to find the ith smallest element in this ever-changing set. Like maybe you need to quickly locate the 10th smallest value or the 500th and so on. We call that element the ith order statistic.
Oh, I see. So it's like finding a specific ranking in a constantly shifting leaderboard.
Perfect analogy. Now, the straightforward but not so clever approach would be to sort the entire dataset every time you want to find a specific rank. But as you can imagine, with tons of data coming and going, that's super inefficient. You'd be spending way too much time just sorting and resorting.
I can see how that would be a major bottleneck. So what's the more clever augmented approach?
Well, instead of resorting every time, we take a red-black tree, which, as we discussed, is already great at staying organized, and we give it just a little boost.
A little boost, how?
We add something called the size attribute to each node in the tree.
Okay, size. What does that represent exactly?
Think of it as keeping tabs on how many internal nodes, meaning nodes that actually hold data, are present in the subtree rooted at that particular node.
Yeah.
Essentially, it tells you how many data elements are hanging out beneath that point in the tree.
So it's like each node is wearing a badge saying, I've got this many descendants.
Precisely. And calculating the size is actually really simple. We just define the size of a node as the sum of the sizes of its left and right subtrees, plus 1 for the node itself. Oh, and we say that the size of a sentinel, which is like a placeholder at the bottom of the tree, is a 0.
Okay, so we've got our red-black tree all decked out with these size badges. How does that help us find, say, the 20th smallest element any faster?
Great question. So the chapter introduces this handy procedure called OS select x.size. It takes two inputs, a pointer to a node, we'll call it x, and the rank I of the element we're looking for. Let's walk through it. First, it figures out the rank of node x within its own little subtree. We can call this rank R, and it's just the size of its left subtree, plus 1 for the node x itself. Now, if this rank R happens to be exactly equal to the rank we're looking for, boom, we found our element right there at node x.
Makes sense so far. But what if the rank we're looking for isn't exactly equal to R?
Then it gets a bit more interesting. If the rank we want, I, is smaller than R, we know the I smallest element has to be hiding somewhere in the left subtree. So we make a recursive call to OS_select, but this time we focus on the left child or X, still targeting the same rank I.
And I'm guessing if I is bigger than R, we do the same thing, but on the right side.
You got it, but there's a little twist. Since we've already accounted for the left subtree and the node X itself, that's R elements total, we adjust the rank we're seeking in the right subtree to be IR.
I see. We're basically narrowing down our search range as we go deeper into the tree.
Exactly. And because the height of a red-black tree is logarithmic to the number of nodes, this recursive hopping from node to node only takes logarithmic time. It's way faster than sorting the entire data set every time.
Okay, so I'm starting to see the magic of this size attribute. We can now zip around the tree, quickly finding an element with a given rank. But what about the other way around? What if we already have a specific element and we want to know its rank?
For that, the chapter provides a procedure called, you guessed it, OS_rank TX. This one takes the entire order-statistic tree, T, and a pointer to our element X as input. It then spits out the rank of that element within the whole tree. Similar to OS_select, we start by calculating the rank R of X within its own little subtree that's just the size of its left subtree plus 1.
Okay, so that's the local rank. But how do we figure out its rank in the grand scheme of the entire tree?
We work our way up from node X toward the root of the tree. As we move up, we keep an eye out for whether the current node is a right child. If it is a right child, it means that its parent, as well as all the nodes in its parent's left subtree, come before it in the in-order traversal of the tree.
So if our node X is somewhere in the subtree of that right child, those elements all have lower ranks.
Exactly. So in that case, we need to bump up our running rank R by adding the size of the parent's left subtree plus 1 for the parent itself. We keep doing this walking up the tree, adding to the rank whenever we hop from a right child to its parent until we finally reach the root.
And this upward climb, like the recursive descent we talked about earlier, also only takes logarithmic time because of the balanced nature of the red-black tree.
Precisely. Both finding an element by rank and finding the rank of an element can be done with impressive efficiency, thanks to our little size friend.
This is all pretty amazing, but there's one thing nagging at me. We've been talking about finding ranks and elements in this beautifully organized red-black tree. But what happens when we start messing with the tree itself? Like when we insert or delete elements, doesn't that throw a wrench in our size calculations?
That's a very astute observation, and it is something the chapter addresses directly. The beauty of this augmentation is that maintaining the size attribute doesn't slow down the red-black tree's normal operations, insertions, and deletions can still be done in that awesome logarithmic time.
Okay, let's walk through that. First up, how do we handle insertions?
When we insert a new node, we first find the right spot for it by traversing down the tree from the root. As we travel down that path, we increment the size of every single node we encounter. Once the new node is nestled in its spot, its size is set to 1 since it's starting out fresh.
Makes sense. We're basically adding one more data element to the count of every node along that path.
Now, red-black tree insertions can sometimes get a little fancy, involving color changes and these cool moves called rotations to keep the tree balanced. But even with those rotations, the chapter shows that updating the size is a piece of cake.
How so?
Well, after a rotation, we only need to adjust the size attributes of the two nodes that were directly involved. And these updates only rely on the sizes of their immediate children. This means we can do it in constant time. It doesn't depend on the size of the tree at all.
So the added work for our size updates is super minimal, even when we're rearranging things in the tree.
Exactly. And since red-black tree insertions involve at most 2 rotations, the total extra time spent managing our size attribute stays constant.
Yeah.
It doesn't affect that overall logarithmic time for insertion.
That's pretty slick. Now, what about deletions? They can sometimes be a bit more involved, right?
You're right, deletions can be a bit trickier. When we remove a node, there's a chance that up to 2 other nodes might move around in the tree as we restore its balance. After we take care of that, we need to adjust the size attribute of every node on the path from the lowest node that moved up to the root.
I see. So we're retracing our steps and decrementing the size because we've taken out a data element.
Exactly. And again, since the height of a red-black tree is logarithmic, this update process only takes logarithmic time. Just like with insertions, those potential rotations don't add much overhead. We only need to update the size of the 2 nodes involved in each rotation, and we can do that in constant time.
So once again, even with the complexities of deletions, the extra work for managing the size attribute doesn't slow us down.
That's right. The overall time for deletion, even with the size maintenance, stays logarithmic, which is exactly what we want.
This whole order statistic tree business is a really neat example of augmenting a data structure. But it makes me wonder, is there some kind of general recipe we can follow to augment other data structures, or is it just a bunch of clever tricks that depend on the specific structure?
The chapter actually lays out a really nice four-step process for augmenting data structures,
Yeah.
like a set of guidelines for adding superpowers to your data organizing tools.
Okay, I'm all ears. What's step one?
First and foremost, you got to pick the right tool for the job. You need to choose an underlying data structure that's already efficient at doing the basic operations you'll need for your application. Red-black trees, as we've seen, are a great choice for dynamic sets because they're so good at things like searching, finding min and max values, and finding successors and predecessors.
So it's like making sure your Swiss Army knife has the basic blades before you start adding on the laser pointer and the fish scaler. What's the second step?
Step 2 is where the real creativity comes in. You need to figure out what extra information, what little tidbits of data you want to store within your chosen structure to enable those new, super efficient operations you're aiming for.
So in our order statistic tree example, that was the size attribute.
Exactly. The trick is to pick something that's not too cumbersome to maintain, but powerful enough to help you do some cool stuff.
Got it. So we've picked our base structure, we've decided what extra information we want. What's next?
Step 3 is all about making sure that our new augmented structure is actually maintainable. We need to verify that we can keep our extra information consistent and correct when we do those basic modification operations on the underlying structure, like inserting or deleting elements. Ideally, we want to do this without slowing down those basic operations too much.
Right. We don't want to add so much overhead that it negates the benefits of our augmentation. So it's like making sure our Swiss Army knife attachments are securely fastened and won't fall off or jam up the works.
Perfect analogy. And as a bonus, it's often preferable if these updates to our extra information are localized, meaning they only affect a small part of the data structure. It's like only need to tighten one screw if you bump your Swiss Army knife, instead of having to disassemble the whole thing.
Makes sense. Okay, so we've got our structure, our extra info, and we've confirmed we can keep things tidy during modifications. What's the final step?
Step 4 is where the real payoff happens. It's time to develop those new operations that our augmented structure can now handle with grace and efficiency. And sometimes, this extra information can even lead to speed improvements in the existing operations of the data structure.
So it's like our augmented Swiss Army knife not only gets new tools, but also makes the existing ones work even better. The chapter then goes on to give us a theorem specifically for augmenting red-black trees, theorem 17.1. What's that all about?
This theorem is like a cheat sheet for knowing when we can safely augment a red-black tree without sacrificing its efficiency. It basically lays down some conditions that, if met, guarantee that insertions and deletions will still be done in logarithmic time.
I'm intrigued. Lay it on me. What are these magic conditions?
First, the attribute we're adding to each node, let's call it f, can only depend on information stored at that node itself, its left child and its right child. This can even include their respective f attributes, so it's a bit recursive. Second, we need to be able to compute this attribute f in constant time, meaning it doesn't depend on the size of the tree.
So it's got to be locally computable from just its immediate family. What does the theorem guarantee if those conditions hold?
If we meet those two criteria, the theorem assures us that we can maintain the f values for all nodes in the tree, even when we're doing insertions and deletions, and all of that will still only take logarithmic time. It's like a seal of approval for our augmentation.
Okay, so how does that actually work? Why do these conditions ensure we don't mess up the red-black tree's performance?
The key idea is that when we tweak the tree structure through insertions or deletions, any change to the attribute f of a particular node will only ripple upwards toward the root. It won't affect other parts of the tree. And because we can compute f for each node in constant time, updating it along that upward path also only takes time proportional to the height of the tree, which we know is logarithmic.
I see. It's like a chain reaction that's contained within a narrow path.
Yeah.
And because those red-black tree rotations also only happen a limited number of times, they don't mess up the logarithmic time either.
Exactly. The limited rotations and that constant time update for f are crucial for keeping things running smoothly. It's all about keeping the extra work localized and lightweight.
All right, I'm convinced. Theorem 17.1 gives us a clear path to augmenting red-black trees safely. The chapter then moves on to a second cool example, interval trees. I've heard these are really useful for things like scheduling appointments or working with timestamps.
Spot on. Interval trees are specifically designed to handle dynamic sets of closed intervals, basically, ranges of values. Think of it as a way to manage a bunch of appointments that each have a start time and an end time.
Okay, that's a really clear example. How do we represent those intervals within a data structure?
We define each interval, let's call it I, by its lower endpoint, I.low, and its upper endpoint, I.high. So for an appointment, I.low would be the start time, and I.high would be the end time.
Simple enough. Now, a common thing we might want to do with intervals is figure out if two of them overlap. How do we determine that?
The chapter gives a really straightforward condition for checking overlap. Two intervals I and I prime overlap if and only if the lower endpoint of I is less than or equal to the higher endpoint of I prime, and D, the lower endpoint of I prime, is less than or equal to the higher endpoint of I. It sounds a bit wordy, but it's basically checking if they have any shared space on the number line.
I see. If they bump into each other at all, they overlap.
Now, there's also this handy concept called the interval trichotomy that the chapter mentions.
Trichotomy. Sounds fancy. What's that all about?
It's just a fancy way of saying that given any two intervals, only one of these three things can be true. They overlap. The first interval is completely to the left of the second, or the first interval is completely to the right of the second. It's a nice way to categorize the relationships between intervals.
Okay, so we've got our intervals defined, we know how to check for overlap, and we've got this trichotomy thing. How do we actually build an interval tree to manage all these intervals efficiently?
We start with our trusty friend, the red-black tree. Each node x in our tree will store an interval, which we'll call x.nt. But here's the key. The tree is ordered based on the low endpoint of those intervals. So if you were to do an in-order traversal of the tree, you'd encounter the intervals in ascending order of their lower endpoints.
Okay, so the low endpoints determine the structure of the tree. Now where's the augmentation part come in?
We add a new attribute to each node called x.max. This attribute keeps track of the maximum value of any interval endpoint, whether it's the low or the high endpoint, within the entire subtree rooted at that node. So it's like each node is broadcasting the furthest point reached by any interval under its command.
That's clever. So how do we make sure this x.max's value stays up to date when we're constantly adding and removing intervals in the tree? It seems like it could get messy.
Actually, it's super straightforward. The chapter provides a simple formula for computing x.max. It's just the maximum of these three values: the high endpoint of the interval stored at the current node, the max value of its left child, and the max value of its right child.
So it's all local information again. Just like with the size attribute in the order-statistic tree, we can compute it quickly just by looking at the node and its immediate children.
Yep. And because it fits those conditions we talked about in Theorem 17.1, we know that maintaining the x.max's attribute won't slow down our insertions and deletions. They'll still be done in logarithmic time.
I love how that theorem keeps coming in handy. So we've built the stripped-out interval tree. We've got the intervals organized by their low endpoints, and each node is augmented with the maximum endpoint in its subtree. What new superpower does this give us?
The main operation that interval trees are famous for is interval search, T-I-I-I. You give it the interval tree, T, and a query interval, I-I, and it tries to find an interval within T that overlaps with your query interval. It'll either give you a pointer to the node containing the overlapping interval, or if it can't find one, it'll return the sentinel of the tree. Think of it like checking if a proposed meeting time clashes with any existing appointments.
I see. It's like a super efficient conflict detector. But how does this interval search actually work? Does it have to check every single interval in the tree? That seems like it could be slow.
That's where the brilliance of the x.max attribute shines. We start at the root of the tree and work our way down. At each node, we first check if the interval stored at that node overlaps with our query interval. If it does, we're done. We found a match.
Makes sense. But what if it doesn't overlap? How do we decide where to go next?
We use the x.max value to guide our search. If the max value of the left subtree is greater than or equal to the low endpoint of our query interval, we know there's a chance we'll find an overlap in the left subtree, so we go left.
It's like the x.max's value is giving us a hint about whether it's worth exploring that direction.
Exactly. But if the max value of the left subtree is less than the low endpoint of our query interval, we know there can't be any overlap there, so we go right instead. We keep doing this going left to right based on the x.max's value until we either find an overlapping interval or we hit the sentinel, meaning no overlap exists.
So it's like following a trail of breadcrumbs that's guiding us towards a potential overlap. And
Yeah.
because we're only going down one path, the search only takes logarithmic time.
You got it. It's a huge time saver compared to looking at every single interval in the tree.
This is really impressive. But how can we be sure that this search process is actually correct? Like, how do we know that by only following one path, we're not accidentally missing an overlapping interval somewhere else in the tree?
That's where Theorem 17.2 comes in to give us peace of mind. It basically proves that the interval search algorithm is always reliable. It guarantees that if the procedure finds a node, the interval at that node definitely overlaps with our query interval.
Okay, that's reassuring. But what if it doesn't find a node? What if it returns the sentinel?
In that case, Theorem 17.2 assures us that we've searched thoroughly and there's definitely no overlap anywhere in the tree. The logic behind this correctness lies in the clever way we decided to go left or right at each step. If we went left, it means there was a genuine possibility of an overlap in that subtree. And even if we didn't find one there, the theorem proves that there can't be an overlap in the right subtree either.
So by following the x.max breadcrumbs, we're guaranteed to explore all the areas where an overlap could potentially exist.
Exactly. And if we went right, it means we were absolutely sure there was no overlap possible in the left subtree. This careful decision-making ensures we're not missing anything.
This is a fantastic illustration of how augmenting a data structure can give us these really powerful new capabilities. It's almost like magic how such a simple addition can make such a big difference.
It's a testament to the ingenuity of computer scientists. They're always finding ways to tweak and optimize these fundamental tools to solve problems in incredibly clever ways.
Well, this has been a fascinating deep dive into Chapter 17 on augmenting data structures. We've covered a lot of ground from order-statistic trees with their size attribute to interval trees with their x.max attribute, and we've even touched upon those handy theorems that help us understand why these augmentations work so beautifully.
It's been a pleasure to explore these concepts with you. Augmenting data structures is truly a fundamental technique that allows us to build incredibly efficient solutions to a wide array of problems.
And who knows what other clever augmentations people will come up with in the future. It's a constantly evolving field. But for now, we've reached the end of our deep dive into Chapter 17, and I feel like we've covered all the major points, theories, findings, and examples. Thanks for joining us.
Until next time.